In the year 1054, something truly remarkable happened here on Earth. A brilliant light appeared in the sky, brighter than any star at night and even visible in broad daylight. In China, it was called a guest star and carefully recorded in written accounts. In Chaco Canyon, New Mexico, some believe its arrival may have been recorded as a pictograph, a celestial event memorialized in stone. And then, without warning, it slowly faded from the sky. But what no one knew at the time was that they had just witnessed the violent death of a star, a colossal supernova 6,500 light years away in our own galaxy, so powerful that it lit up the Earth's sky and was seen across the world. And here's the thing, it never truly disappeared. It's still out there, a storm of gas and dust tearing across space at over 1,000 kilometers per second, an expanding cosmic scar, the Crab Nebula. We can still see it today, glowing, tangled, beautiful. But what's truly fascinating isn't what you can see. It's what's hiding at the heart of it, because buried in the centre of this ancient explosion is one of the most exotic objects in the known universe. Something so dense, so compact, so powerful, it breaks our everyday understanding of space, time, and matter. A pulse, a flicker, a cosmic heartbeat that stunned astronomers and sparked one of the most controversial Nobel Prize stories in history. And in this video, we're going to peel back the layers to understand this most extreme of objects, using nothing more than high school maths and physics, to figure out what this thing is, how it formed, and how it's possible for something so small to unleash 200,000 times more energy every second than the sun, from a sphere no larger than a city. This is a story of a pulsar, a dead star that became one of the most extreme engines in the cosmos, born in a supernova, powered by rotation and pulsing with unimaginable energy. This is where death meets raw cosmic power, so buckle up and enjoy the ride. When a massive star reaches the end of its life and explodes, its core can collapse into something extraordinary, a neutron star, just over 10 kilometers wide, yet heavier than the sun. A single teaspoon would weigh over 1 trillion kilograms. These stellar remnants warp space, twist time, and defy all common sense. But here's the real question. If something this extreme actually exists, how would we know? Can we just point a standard telescope at the night sky and hope to see one? To begin to answer these questions, consider a neutron star with a surface temperature of 1 million Kelvin. That's roughly the estimated surface temperature of the neutron star at the centre of the Crab Nebula. To estimate how much energy such a star emits every second, its luminosity, we start with the Stefan-Boltzmann law, which gives us the power radiated per square metre of surface area. That's called the radiative intensity, and it's given by the following equation, I equals sigma T to the 4, where sigma is the Stefan-Boltzmann's constant, which is approximately 5.67 times 10 to the minus 8 watts per metre squared K to the minus 4, and T is the surface temperature in Kelvin. This equation tells us how much energy a single square metre of the star's surface emits every second. But to get the total luminosity, we need to multiply this by the entire surface area of the star. We can write an equation for the luminosity as L equals I times A, where I is the radiative intensity and A is the area. For a sphere, the surface area is equal to 4 pi r squared, meaning that the luminosity can be written as 4 pi r squared sigma T to the 4. This gives us the total energy output per second, the star's luminosity, in watts. So with a known temperature and an estimated radius, we can now calculate the luminosity of a neutron star. We'll use a radius of 13 kilometers, which is 1.3 times 10 to the 4 meters and is typical for an average neutron star. And if we then sub this along with the temperature and Stefan-Boltzmann constant into the luminosity equation, we find a value of 1.2 times 10 to the 26 watts, which is about 1/3 the luminosity of the sun. Now, you might think, not bad, right? You might expect that such an object would be visible through a standard telescope. But there's an issue. Firstly, the neutron star at the centre of the Crab Nebula is 6,500 light years away. And secondly, whether we can actually see that energy depends not on just how much is emitted, but on what kind, specifically the wavelength of the radiation. An object like a star behaves like an ideal black body, meaning it emits a broad spectrum of electromagnetic radiation, a range of wavelengths, each with its own intensity. However, there's always a peak wavelength at which emission is strongest for a given temperature. We can determine this peak using Wien's displacement law, which tells us the wavelength of maximum intensity for a blackbody radiator at a given temperature, and it's calculated using the following simple equation. If we take the surface temperature of our neutron star and sub it into the Wien wavelength equation, we find that the wavelength corresponding to maximum intensity is 2.9 times 10 to the minus 9 meters. This is deep in the X-ray part of the electromagnetic spectrum, far beyond what the human eye can see. So, despite all that power, the neutron star would be incredibly faint in visible light, but very bright in X-ray light. So that suggests that an X-ray telescope would be ideal for spotting them. But maybe there are other subtle clues, hints written into the very radiation that these stars emit. You see, near the surface of a neutron star, gravity is so intense it doesn't just pull on matter, it pulls on light itself. According to Einstein's general theory of relativity, light escaping a strong gravitational field gets redshifted. Its wavelength stretches and its frequency decreases, causing a shift towards the red end of the spectrum, hence the name. This effect, known as gravitational redshift, means that photons lose energy as they climb out of a gravitational well, arriving with a longer wavelength and lower frequency than when they were emitted. The equation that describes this gravitational effect takes the following elegant form. Here, Z is the redshift factor, essentially the fractional increase in wavelength, G is the gravitational constant, M is the mass of the object, R is the radius from which the light is emitted, and C is the speed of light. For a neutron star with a typical mass of 1.4 times that of the Sun, and a radius of about 13 kilometers, we can plug the values in and we find a Z value of 0.21. In other words, the wavelength of the light increases by approximately 21% as a result of the gravitational redshift. And this energy loss isn't just a theoretical curiosity, it has measurable effects on the spectral lines of atoms near the star, which get redshifted in a characteristic and predictable way. Even though neutron stars are mostly composed of neutrons, they can still have a thin atmosphere just a few centimeters thick, made up of ordinary atomic nuclei, and this atmosphere may contain traces of heavier elements such as iron, either left over from the original star or deposited by fallback material after the supernova. And it turns out that iron is especially useful because its highly ionized X-ray absorption lines are sharp and well characterized. We know precisely what wavelengths they should appear at. So if we observe these same lines from a neutron star, but find them shifted to longer wavelengths, it means that the photons lost energy escaping from the gravitational field. Detecting such a redshift in absorption lines provides a rare direct observational handle on the extreme gravity at the surface of a neutron star. But gravity isn't the only extreme feature. Neutron stars also spin, and often at breathtaking speeds. That's because if the star they formed from was spinning, even slowly, then as its core collapses, conservation of angular momentum causes the rotation to speed up dramatically. It's the same principle that we observe when an ice skater spins faster when pulling in their arms, and we can quantify this for a neutron star. For example, take a star that rotates just once every 100 Earth days, slow by stellar standards, but as the star collapses, that sluggish spin transforms into an incredibly rapid rotation. By way of example, if we consider a star whose radius reduces from around 1 million kilometers to just 13 kilometers, conservation of angular momentum kicks in and we can actually calculate the new rotation rate. The angular momentum of a rotating object is given by the equation L equals I omega, where L is the angular momentum, I is the moment of inertia, and omega is the angular frequency. For a solid sphere of uniform density, the moment of inertia is 2/5 times mr squared, And if we combine this with the angular momentum equation, we get the following expression. Now, if no external torques act on the collapsing star, then L is conserved, and we can write this as L initial equals L final. If we then use the expression for the angular momentum of a rotating sphere, we can write the conservation condition in the following form, where Ri and omega I refer to the initial radius and the initial angular frequency, and Rf and omega f refer to the final radius and the final angular frequency. If we then cancel off terms from both sides, we find the following expression, and if we then rearrange for omega f, we find the following equation for the final angular frequency of the neutron star. We see that the final spin rate depends entirely on the initial spin and the change in radius. Okay, so let's now work this out. If we assume that before the collapse, the rotational time period was 100 days, which corresponds to 8.64 times 10 to the 6 seconds, we can then calculate what the initial angular frequency is using the relation omega equals 2 pi over t, in which case we find 7.27 times 10 to the minus 7 radians per second. If we then take the initial radius as around 1 million kilometers and assume that after the collapse the radius has reduced to 13 kilometers, we're then in a position to calculate the final angular frequency. Plugging all the numbers into our equation, we find a final angular frequency of 4.29 times 10 to the 3 radians per second. We can convert this into a rotation frequency in revolutions per second by using the fact that f equals omega divided by 2 pi, and we find a value of 685 Hz, which is staggering. This means that as a result of the collapse, the neutron star is now spinning 685 times per second, and that's from a star that was barely turning, just once every 100 days. To show just how extreme this spin is, let's compute the speed at the equator. We can do this by using the equation v equals r omega, where r is the radius and omega the angular frequency. And if we plug in the numbers, we find that the linear speed at the surface at the equator is 5.58 times 10 to the 7 meters per second, which is 0.186 times the speed of light. So the surface of the neutron star is moving at nearly 19% the speed of light. That's an astonishing spin rate. But could a neutron star spin even faster, or is there a speed limit? Well, it turns out there is, because if the neutron star spins too fast, then gravity won't be strong enough to hold the star together. So let's quickly take a look at this breakup limit. To be precise, breakup occurs when gravity can no longer provide the required centripetal acceleration. We can write this as a mathematical statement, where the left-hand side represents the centripetal acceleration and the right-hand side represents the gravitational acceleration. If we then rearrange this, we have that omega max is equal to the square root of gm over r cubed. And this tells us the maximum angular frequency for a given mass and radius neutron star. If we then plug in the mass and the radius we used before, we find that omega max is equal to 9.2 times 10 to the 3 radians per second, and this corresponds to 1,465 revolutions per second. Any faster and the star would tear itself apart. Our neutron star was spinning at 685 Hz, which was below this, but not by much. However, spinning fast isn't the only thing a newborn neutron star does. We also know that as a star collapses to form a neutron star, its magnetic field intensifies in spectacular fashion. But why? Well, firstly, most stars have a magnetic field that resembles a bar magnet with north and south poles. And when a star collapses, it compresses not just its mass, but also the magnetic field lines that thread through its core. In a highly conductive plasma, like the interior of a star, magnetic field lines are effectively frozen in, meaning they move with the plasma as the star collapses. So, when the star shrinks, the field lines are dragged closer together. The result, a much stronger magnetic field. This dramatic intensification can be understood through the principle of magnetic flux conservation. In a plasma with extremely high electrical conductivity, as found in the core of a collapsing star, magnetic field lines are locked into the fluid. They can't slip, break or diffuse away. As a result, the total magnetic flux passing through any surface that moves with the plasma remains constant over time. Now here's the catch. The surface area of a star decreases dramatically as it collapses. So if the same amount of magnetic flux is being squeezed through a smaller and smaller surface, the only way to conserve it is for the magnetic field strength to increase. To visualize this, consider a surface of area A. Then imagine magnetic field lines passing at right angles through the surface. The magnetic field strength B is proportional to the density of those lines, and the magnetic flux is simply the product B times A. Now, if the flux is conserved during collapse, we can write this mathematically as BIAI equals BFAF, where I refers to initial and F refers to final. And if we rearrange for BF, we get the following expression. This makes it clear. As area shrinks, field strength must grow. Now, for a spherical star, the surface area is given by 4 pi r squared, and so our flux conservation equation can be written in the following form. And if we then cancel terms and simplify, we find the following result, expressed in terms of the initial and final radii of the star. Now, again, suppose the star collapses from an initial radius of 1 million kilometers to 13 kilometers. If the initial magnetic field strength was 0.001 Tesla, which is a typical value, then the final magnetic field strength becomes 5.92 times 10 to the 6 Tesla. That's roughly 6 million Tesla, or over 100 billion times stronger than the Earth's magnetic field. It is immense. Now, clearly, fields this strong don't just sit there quietly. They force charged particles to spiral around the magnetic field lines, emitting electromagnetic radiation. More specifically, charged particles stream outwards along open field lines near the magnetic poles, producing cone-shaped beams of electromagnetic radiation. As the neutron star rotates, these beams sweep through space like a rapidly rotating lighthouse, and if one crosses Earth's line of sight, we detect a pulse. However, if the beam never sweeps across the Earth, then we will never observe this signature signal. Out of all the electromagnetic emissions, radio waves are often the easiest to observe. X-rays and UV are easily absorbed or scattered by interstellar gas and dust, but radio waves pass through with minimal interference. Crucially, they also penetrate Earth's atmosphere, allowing astronomers to detect them using ground-based radio telescopes. That makes them especially useful for spotting distant neutron stars. If a radio source is compact, strongly magnetized, and shows rapid variability, such as pulses every few milliseconds, it's strong evidence for a pulsar, a rotating neutron star whose narrow beams of radiation sweep past Earth like a cosmic lighthouse. And yet for decades, no one had seen one, despite all the theoretical predictions and all the telltale signs of crushing densities, gravitational redshift, rapid rotation, and extreme magnetic fields. These objects remained undetected. But why? Well, because no one was looking in the right part of the spectrum. Now, the concept of ultra-dense stellar remnants can actually be traced back to Lev Landau. In early 1931, while in Zurich, Landau drafted a paper on the theory of stars, speculating that stars might reach such extreme densities that atomic nuclei come in contact with each other, collapsing into a single gigantic nucleus. A more concrete proposal came in December 1933, when Walter Baade and Fritz Zwicky suggested that supernova explosions could produce compact remnants composed largely of neutrons. In a pair of groundbreaking 1934 papers, they argued that the immense gravitational energy released during a supernova explosion could be explained if a supernova represents the transition of an ordinary star into a neutron star, an entirely new type of object. This was the first modern theoretical prediction of neutron stars as we understand them today. The idea was so exciting that it even found its way into newspaper comics, a sign of how deeply it captured the public imagination. Yet for decades, neutron stars remained a theoretical oddity, bold enough to intrigue scientists, but lacking the evidence to convince them. It wasn't until 1962 that the tide began to turn, with the detection of Scorpius X1, the first confirmed source of X-rays from beyond the solar system. It was discovered by an X-ray detector aboard a sounding rocket, launched by a team led by Riccardo Giacconi. Though its true nature wasn't immediately understood, this marked the dawn of X-ray astronomy, and the beginning of direct observational evidence for exotic, compact objects like neutron stars. Even the faint star at the heart of the Crab Nebula had been seen in visible light as early as 1942, when Rudolf Minkowski examined its spectrum and called it extremely unusual. It was catalogued as peculiar, but with none of the other telltale signs we now recognise of a neutron star, optical data alone couldn't uncover its true nature. The evidence was there, it was just buried in the wrong part of the spectrum. If anyone was going to stumble upon a neutron star in those early years, it would have been the radio astronomers, though they didn't yet know what they were looking for. However, most radio telescopes were tuned to detect steady radio emissions, not pulses that flickered on millisecond timescales, and so neutron stars remained hidden in plain sight, elegant theoretical constructs still waiting for their moment to be confirmed. That all changed in the mid-1960s. At the University of Cambridge, a team led by Anthony Hewish set out to study rapid fluctuations in radio waves from distant cosmic sources, variations thought to be caused by irregularities in the interstellar plasma and the solar wind. To detect these subtle changes, they built a specialised radio telescope capable of capturing signals that varied on timescales of less than a second. They weren't searching for neutron stars, but without realising it, they had constructed the perfect instrument to uncover them. Among those operating the telescope was a young graduate student named Jocelyn Bell. In November 1967, as she manually inspected the data, she noticed something unusual. She found a signal that repeated with astonishing regularity, about once every second. This wasn't noise, it wasn't an instrument glitch, and it didn't fit the random fluctuations caused by interstellar plasma. After ruling out terrestrial interference and verifying that the signal moved with the stars, she convinced the rest of the team that this was a real astronomical source. In 1968, the discovery was announced, a new kind of object, a source that emitted precise repeating pulses of radio waves. They named them pulsars. But what exactly was a pulsar? What had Jocelyn Bell uncovered? Well, neutron stars quickly emerged as the leading candidate, though astronomers first had to rule out other explanations, for example oscillating white dwarfs or binary systems. However, one clue that stood out was the astonishing stability of the pulses. Week after week, they kept time with near atomic precision. And in astronomy, that kind of consistency usually means one thing: rotation. These had to be spinning stars. Not orbiting, not wobbling, but rotating. But what kind of star could spin that fast? To answer this question, we refer to our earlier result, where we saw that the maximum angular frequency of a rotating neutron star is given by the square root of gm over r cubed. Now, assuming a constant density spherical star, we can write the mass as ρ times v, where ρ is the density. And then if we sub in the volume of a sphere, we find the following expression. If we then sub this mass expression into our expression for omega, we find the following relation, which simplifies to the square root of 4/3 g pi rho. And so we see that the maximum angular frequency only depends on the density of the neutron star. Now we can express this in terms of the time period, since t equals 2 pi over omega, and if we sub in the expression for omega, we find that the time period is equal to the square root of 3 pi divided by g rho. Finally, we can rearrange for the density ρ, and so we see that if we know the time period of rotation, then we can estimate the minimum density that the rotating object must have. Now, for a pulsar with a 1 second period, like the one found by Jocelyn Bell, The minimum density is around 1.41 times 10 to the 11 kilograms per meter cubed, which is just barely compatible with the model of a rotating white dwarf star, which some astronomers try to argue. But when astronomers found pulsars spinning not once per second, but once every 30 milliseconds, this shifted the minimum density to around 1.57 times 10 to the 14 kilograms per meter cubed, and this extremely high density couldn't be explained by a rotating white dwarf. Rather, there was only one kind of object that had been proposed to have such high densities, a neutron star. Once that was accepted, everything else fell into place. The precise regularity of the pulses came from the star's rotation. The pulse itself came from a narrow beam of radio waves emitted along the star's magnetic axis. For her discovery of the first pulsar, Jocelyn Bell, then a 24-year-old graduate student, meticulously combed through kilometres of chart recordings, spotting a signal no one else noticed. She verified it, defended it, and convinced her colleagues it was real. It was, without question, one of the most important astronomical discoveries of the 20th century. But when the 1974 Nobel Prize in Physics was awarded for the discovery of pulsars, it went not to Bell, but to her supervisor Anthony Hewish, who shared the prize with Martin Ryle. Bell's name was not even mentioned. At the time, it caused quite a stir. The famous British astronomer Fred Hoyle publicly accused Hewish of pinching the credit, calling it a scientific scandal of major proportions. To this day, many scientists regard it as one of the most glaring oversights in Nobel history. And yet, Bell herself handled it with extraordinary grace. In 1977, she said, "Nobel Prizes are for senior scientists. It would demean the prize if they were awarded to research students." But in more recent years, she has spoken more candidly about the snub, describing the decision as part of a wider pattern of systemic bias. In 2018, over 50 years later, she received the $3 million Breakthrough Prize in Fundamental Physics for fundamental contributions to the discovery of pulsars and a lifetime of inspiring leadership in the scientific community. She donated the entire sum to fund scholarships for women, minorities, and refugees in physics, turning recognition into impact. Her story reminds us that pulsars aren't just cosmic wonders. They're part of a deeper human story, one of discovery, perseverance, and purpose. And so, to end, let's return to the mystery at the heart of this video, perhaps the most astonishing fact of all. How can a dead star, no bigger than a city, outshine the sun 200,000 times? After all, a pulsar is what's left behind when a star dies. To answer this question, we'll focus on the Crab pulsar, the tiny, rapidly spinning neutron star born in the supernova of 1054. And as we've already seen, pulsars emit radiation across the full electromagnetic spectrum, which can be dramatically revealed when we collect light of different wavelengths. And the fact that the Crab pulsar shines so brightly across the electromagnetic spectrum tells us one thing very clearly. There is an enormous reservoir of energy driving the emission. But where does this energy come from? Well, the answer is the star's rotation. As the neutron star spins, it loses energy, and as a result it slows down. This slowdown is gradual, but measurable. Over many years, astronomers have tracked a very slight decrease in the rotation frequency of the Crab pulsar, and that tiny change gives us a way to calculate how much rotational energy is being lost and to estimate the power output of the pulsar. To do this, we'll start by approximating the star as a uniform solid sphere, which, as we saw earlier, gives a moment of inertia equal to 2/5 mr². It then follows that the rotational kinetic energy, which is equal to half I omega², can be written as 1/5 mr² omega². Now, if you recall, the angular frequency omega is related to the surface speed, which we're going to call v subscript s, by the equation omega equals v subscript s divided by r. So we can write the kinetic energy as half mv². This expression gives the total rotational energy directly in terms of the surface speed. Okay, so let's use values appropriate for the Crab pulsar. we will assume a mass of 1.4 solar masses, a radius of 13 kilometers, and a time period of 0.033 seconds. This corresponds to a surface speed of 2.47 times 10 to the 6 meters per second. And if we then sub this value into the kinetic energy equation, we find an energy of 3.42 times 10 to the power of 42 joules. And this represents the total rotational kinetic energy of the Crab pulsar. But how quickly is that energy being lost? Well, experimental data gathered over 45 years shows that the pulsar's rotational frequency has decreased by approximately 0.5 Hz over that 45-year period. And assuming a linear slowdown, this implies that the surface speed decreases by a tiny fraction in each rotation, equal to -4 times 10 to the minus 13. We can now calculate the corresponding change in energy. To do this, we first consider how the energy changes when the surface speed changes by delta V. If we then subtract the original energy K, we are left with the following expression for delta K, which represents the change in kinetic energy. Next, if we form the ratio delta K over K, we get the fractional change in energy, and then we can neglect the second squared term since this will be negligible compared to the leading order term, and so we're left with 2 times the fractional change in surface speed during one rotation. If we then rearrange for delta K, we find the following compact expression, and this is what we'll use to determine the energy lost during a single rotation. As we've already seen, the fractional change in surface speed is roughly equal to -4 times 10 to the minus 13, and the original kinetic energy is 3.42 times 10 to the 42 joules. If we plug in these numbers, we find that the energy lost per rotation is 2.7 times 10 to the 30 joules. And since each rotation takes just 0.033 seconds, the rate of energy loss, aka the power, is given by P equals delta K divided by delta T. And if we sub in the numbers, we find a power output of roughly 8 times 10 to the 31 watts, or joules per second. That is a staggering power output, roughly 200,000 times the energy radiated by the sun each second. And what's amazing is that this back of the envelope estimate actually gives the right order of magnitude, though it's believed the true value is closer to around 100,000. And to think, all of this is coming from a tiny spinning ball of nuclear matter, just 13 kilometers across, wrapped in a magnetic field over 100 billion times stronger than the Earth's, surrounded by a storm of particles flinging radiation across the cosmos. This is what was born from that ancient explosion in 1054. This is what lies at the heart of the Crab Nebula. Not the corpse of a star, but its transformation, a pulsar, a beacon of unimaginable density and power, still spinning, still shining, nearly 1,000 years later. And through our telescopes we still see its afterglow, a tangle of gas and dust, a cosmic scar stretching across space, a silent echo of the day the sky lit up. And incredibly, this is just the beginning, because scattered across the universe are even stranger, more powerful beasts, magnetars, whose magnetic fields can tear atoms apart, quasars, brighter than 1 trillion suns, and black holes, from which not even light can escape. But these will have to wait till next time. And if you're curious to explore the physics behind these cosmic monsters, from spinning neutron stars to the equations that govern fields and forces, then I highly recommend checking out today's sponsor, Brilliant. Brilliant offers interactive courses across maths, physics, computer science, data analysis and more, all designed to help you build real understanding through active problem solving. Instead of passively watching videos, you'll test your thinking, explore ideas hands-on, and develop your intuition, a method shown to be up to 6 times more effective than lecture-based learning. Courses are created by award-winning educators and experts from places like MIT, Caltech and Google. One course I particularly enjoy is exploring data visually. In astrophysics, we often rely on patterns in messy, complex data, from pulsar timing to the structure of galaxies. This course helps you learn to spot those patterns, extract meaning, and communicate insights clearly, all through interactive visual learning. And right now, you can try everything Brilliant has to offer completely free for 30 days. Just head to brilliant.org/physics explained, scan the QR code on the screen, or click the link in the description. You'll also get 20% off an annual premium subscription if you decide to stick around. So thanks for watching, and until next time, goodbye. And as always, a massive thank you to all my patrons, and a special shout out to the following, who have been incredibly generous with their support. Thank you so much. I couldn't do it without you.